Hola de Barcelona. It's great to be able to present here today at ODSC. And I'd like to talk a little bit about scaling machine learning with data mesh. The general kind of idea here is that, just to give you a little bit of context, is that we want to kind of illustrate how scaling data management and different components within the ML ops and the data space using data mesh tenants can improve or like really can expand what you can do with machine learning. And so just to kind of kick off, I'm going to go ahead and share my slides. I know sometimes some of these slides are actually can be a little bit difficult to view. So if you need to do that, you can go ahead and access these publicly. Also, I cite some really excellent sources in the slide deck, and I think that those people definitely deserve credit. Cool, so let's get into it. I think every good like machine learning problem solving, it starts with a really good story, right? You know, we really need to think about the product first, like what kind of thing are we trying to solve before we just jump into it. And our story kind of begins with a very traditional approach to how we're going to solve this problem. And then we're going to kind of talk about how we're going to evolve into kind of the data mesh paradigm from our more traditional approach. Cool. So as I originally started thinking about this, I was sitting in my house deciding whether or not I should put the air conditioning on and how much that's going to cost me from an energy perspective. And I kind of took that very kind of small perspective, and I thought, well, what is everything in my house actually using, right? Like what kind of consumption is coming out of everything? And then I thought, wow, if you could do this for every household, I wonder if there's something even bigger here. And so I came up with this use case, this user story, if you will. So if I were an energy company, I'd like to accurately predict what residential energy consumption is so that we can adjust the amount of power available in the grid in order to avoid waste and potential failures, right? Because in many ways, a power grid is kind of like that you're filling up constantly, right? If you fill it up too much, it overflows, that water is just wasted. In the same way, more or less, I'm not an electrical grid expert, but that's kind of how it works. So if you can predict the amount of water, or in this case, electricity that's being used and the amount that you need to put back in, you can also predict what types of renewable versus non-renewable resources you want to bring on, right? Because you want to try to use as few amount of non-renewable energy as you need to, right? So you don't want to overfill the bucket and use too much. So in order to do this, a very super clever paper, and it is cited in my sources there, someone has already thought of this. And basically what we want to do is to set the stage for the use case that we're trying to solve is we want to focus on anomaly detection, energy spikes, in a closed loop system, leveraging a convolutional neural network. So we're going to do a hybrid with LSTM, long short-term memory, to demonstrate the benefits of adopting the data mesh paradigm across a multi-plane data platform in the machine learning operations. We're going to talk a little bit about model experimentation and production, and then also what these common affordances are and how they're going to actually help us solve this problem, right? And also future-proof, like problems that we're going to solve. So the first thing is we kind of have to figure out like, okay, so Shawn, you've given us like, what are we going to do with this like sensor data that comes from inside a smart home? You know, it's measuring individual appliances, and it's, you know, just really basic sensor data, very homogeneous. And so in order to actually use this in a CNN, what we really need to look at is like, how can we kind of like spatially represent this data over time series, right? So spatially and temporally. And so what we could do is kind of look at like 60-minute intervals, and then we can create like a heat map, and we can leverage this over and over again. And we can kind of say, okay, well, this is the image that we're using to push through our CNN. But we can't stop there, right? Because we also have our LSTM and our FC layer. And so the next thing is, so once we kind of have generated all of our images from our consumption data, right? So we have all of our household appliances, and these are all of our features. Maybe each of the meters is a different type, like it's a washing machine, or it's an air conditioner, or a heating unit. And basically the CNN is more or less used to remove the noise and take into account like the correlation between the multivariate variables. And the LSTM models like temporal information and maps time series data into separate spaces, right? Because then we want to be able to generate the predictions by passing it through kind of our final like FC layer here, right? So CNN, our LSTM layer, and then finally our bookend here with FC layer. So if we do this and we can accurately predict power consumption, and we do this on a very small scale at first, right? Just a few households. Then we can say, okay, I can serve up this model in a predictive way, and I can use it to regulate the power inside my power grid. And then I regulate the power based on the model, and then I feed back through, and here's our closed loop. And then we're feeding it right back in. And then we're learning from what we did, and we're kind of like reinforcing this once again, right? Because we know how much consumption is actually used versus what we predicted. We don't really have to think much about it. So we can just continually like improve the modeling. Cool. So that's more or less like how, like that's kind of just setting the stage for what we're doing here, right? This is the use case that we're going to use throughout the presentation, and I'm going to reference back to it. And we're going to talk about like what the evolutionary journey is going to look like, leveraging this specific use case. So hold that in your LSTM, right? All right. So traditionally, I think we approach this from having kind of like a data and analytics team and a machine learning and data science team, right? And they are in separate silos, but they do talk to each other, right? And I think, you know, that actually works. There's nothing wrong with that particular problem or particular like approach. But from this, just like Conway's law, right? So our operating model is going to now reflect our architecture and vice versa. We are going to create a separate data monolith that maps to our data and analytics team, right? That team is responsible for it. And as you can kind of see here, it's nothing fancy. Like we have our smart home interface, we have a stream and event store, puts it into a data lake, does some ETL, puts it in like a centralized data warehouse. And this works totally fine, right? We have a very small subset of like houses here, and there's like no issues at all. Cool. And then we say, okay, let's do some algorithmic experimentation on our ML platform. That team has like ML ops folks, data scientists, that kind of thing. They build their own separate monolith, and it just takes an input from the centralized data warehouse, which is the output, and does some feature engineering, pops it into a feature store. We have our machine learning orchestrator. I mean, this could be any number of things, right? It could be Qflow, you could use MLflow, doesn't really matter, but we basically like build the model that we just talked about, and we run the data through, right? And then we feed it back into, we feed the predictive model back into we serve it up to the power grid, and great, everything works, no problems, right? But one thing, it never really stops there, right? So you kind of always have this, you know, like situation where you say, okay, you know, I've built this once, I've done my experimentation, I figured out how to productionize it, yay. It's working fine, right? It's working fine for the small subset of households that I have. But then some new requirements emerge, right? So here comes the dragon, right? And the new requirements fall into 3 different categories, more or less, right? The first one is, could we actually get better modeling if we leverage information about the customer's household, like occupancy, or the customer's household behavior even? We could take it that far. Yeah, probably. I mean, that's a good guess. That would be a really interesting feature that we could add, right? And we could run through our modeling cycle, our modeling pipeline. And okay, great. So now we need to add a variety of data. But this type of data like is very different from the energy sensor information that we're bringing in. So our team that was previously handling that sensor data, they don't really understand this like operational household data. It has a different schema. You know, it comes from like a different data source even, right? It's more of like a relational store. So there's a little bit of issues there. And then we also now they said, you know, everything's working amazing. So now your challenge is let's rapidly expand the number of households, right? Because a small subset of households isn't really going to give us enough bang for our buck here, right? Like we've proved it once and we know that it works, and we've done our happy path, but now let's start to scale it out, right? Let's do more households and right. And so that's, so now suddenly we have more of our volume. And now we also need to add more sensors per household. So the more features that we can get in, the better in a way, right? Because we're going to be able to analyze which of those features at any given point in time are going to be more or less relevant to predict the energy consumption, right? So for example, like maybe during the winter, a sensor on the heater is more predictive than, or a feature that is based on the heater's consumption is more predictive than the air conditioning, and vice versa for the summer. Different things like that, right? So we just want to get more fidelity and greater amount of features that we can run through our model. And finally, we need to add more sensors per household to explore additional features to use in modeling. So now we kind of have this problem that we're kind of moving into kind of the big data world, right? We have volume of data, variety of data, and velocity of data that's coming in, right? So it's coming in faster, there's more of it, and there's a greater variety. So unfortunately, that is not going to scale well with our two monoliths for a couple of reasons, right? So we have kind of the dragon is attacking here. We got to figure out how to get around this. Because for some period of time, we can definitely throw more hardware at the problem, right? We can keep, scaling different features. We can, keep expanding the size of our data warehouse. We can add extra nodes, and we're kind of going to reach a breaking point, right? Where there's going to be some bottlenecks that start to kind of crop up. And not only do the bottlenecks exist in the architecture itself, but also in the operating model, right? Because as we start to manage more and different kinds of data, we suddenly need to, we're asking this smaller team that is managing the energy consumption to now also learn all about this other domain of data of customer information, right? So their cognitive load increases pretty dramatically. And we could add more people to that team, but then we get situations where suddenly we have like a 15 to 20 person stand up, or even if we split those teams, the synchronization between the two teams starts to become a bottleneck because they're both working on the same things in the same area because we're highly centralized. So it also doesn't really scale very nicely when we start bringing in more data. And there's only so many people we can throw at the problem and so much hardware that we can throw at the problem. So now we have kind of reached this like critical inflection point of where, we need to really figure out how we're going to solve this problem. Like, how could we do this? So we know we can't stay with what we currently have. So we need to really rethink a couple of different areas. So how can I fix this problem before it's too late, right? So as I continue to add more households and I continue to add more people, I'm going to reach this critical breaking point. And the oracle here is you must use the power of data mesh, right? So what even is this data mesh? So data mesh was first coined by Zhamak Dehghani. And basically she said that it's a decentralized, right? So we're highly centralized, now we're decentralized socio-technical approach to manage data at scale. What to emphasize here is the social or socio and technical approach. So we're going to change our operating model, but we're also going to change our architecture. And it resolves these by distributing data ownership, right? In the previous example, if something were to break, the same people that handled the customer data were probably the same people that handled the energy data that handled all of the other pieces of data. So everyone is accountable, which probably means that no one's accountable. So that's kind of a problem. We want to give some ownership. We also want to give the users data ownership and empower them with self-service tools, right? So we have a very static, tightly coupled model with the centralization, but we want to be able to actually spin up as many different types of models and data sources and that kind of as we possibly can. And so we need to do that like kind of in a self-service way. And of course, we need some governance for sure, but we need it to be federated, right? Because governance is going to be a little bit different depending on the type of data, if it's machine learning, that kind of thing. So if this is the way, like how do we get there, right? So we go to the wizard and kind of ask, like, what is the path that we shall follow? And we can actually kind of trace it in the following way, right? If we first start by looking at it in a domain-driven way, we can, and then we look at each piece of this as it's broken into domains, and we'll talk about this in more detail. And then each component, each architectural quantum, like each basic building block of your system, is a product. Then we can understand all of the capabilities we need and start to generate a self-service data infrastructure with a platform. And finally, all of this can be regulated such that all of these individual pieces are interoperable by setting some basic standards at a top level data governance level. So domains. So since data mesh is very focused on bringing business value, the data mesh partitions data around actually business domains and data ownership to the domain teams. So whereas before everyone was responsible for all of the data, now only specific people are responsible for specific domains, and therefore they are only responsible for their part of the data, right? Now, of course, they can understand all of the data around them, but they're specialists and they're very much like the owners of this data. And the same is also said for modeling, right? So these people who are building our hybrid model, they're also the experts in this area. They understand like energy prediction. They understand how to change the hyperparameters and how to tune the model. So they are the experts for this thing, right? They're not experts of everything. They're experts of specialists in this specific area. So let's break it up. Now, typically you're going to have in a normal use case, you're going to have a whole bunch of different use cases, and you're going to have therefore a whole bunch of different domains in a real life scenario. In this case, just for illustrative purposes, let's just break it down into energy and customer, right? So our energy domain manages all of those consumption, those meters, that kind of thing. And our customer, that manages like our customer household information, right? Our operational data there. And of course, energy also manages the prediction models. Okay, now we have our domains, but now we need to so we've started at the top level, so we've broken it apart one way. So now let's build two separate trees here, right? So let's break it apart again. And let's break it up into different data products. So what do we need to do? Well, it needs to be, all these data products need to have these common characteristics, need to be discoverable. You know, can I find this data product? Can I look it up in a data catalog? Does it live in the feature store, right? Is it addressable, right? Where can I find it? Is it trustworthy? Am I measuring the quality of this data? I mean, is this model, you know, is there any drift in this model? Like how, you know, can I trust it? It's self-describing, right? So it's not many different things. It is one specific thing and it does just that thing, right? And so that's how we want to separate it. Is it interoperable, right? Can I plug and play this particular data product with all of my other data products? And of course, is it secure, right? And that also applies for both data, like encryption with PII, PHI, and we also need to make sure that the models that we're serving are also secure, right? There's different ways of actually like kind of hacking the models, and we need to make sure that those are secure in different ways. So if we were to do this, we would then have our domain energy here. We would have our energy consumption. This is just basically a simple data product that provides the energy consumption. That's all it does, nothing fancy. Same way with the customer household. Just it simply provides that well-curated raw data that's prepared for feature engineering. And then we have our grid consumption prediction, which is going to be like our model training, right? So the flow that we saw earlier. And that's going to serve it up. And then of course, feed back into, that's going to be our multiplane. Now, going back to our use case, I know we've kind of drifted a little bit, so I just want to like bring us back. Basically, again, we want to kind of break this down. And the way that we can break this down is by different types of data products in the system, right? So there's source aligned domain data, and that's going to be energy consumption and customer household. Now that's going to be your data engineering, right? That's going to be kind of your airflow orchestration, your ETL, and it's going to be well curated and prepped for feature engineering and for modeling. And it just does that one little thing. That's all it does, right? And then we're going to have our grid consumption prediction. So this is our more complex kind of like ML, kind of like multiplane consumer aligned data product. And a consumer aligned data product is basically analytic data transformed to fit the needs of one or more specific use cases, right? And the source align data product is reflecting the business facts generated by operational systems, right? So it's very kind of like native data product. And so we kind of have this like little blend of multi-plane consumer aligned data products because our grid consumption prediction not only exists in the analytics plane, like the consumption and the household, but it's also leveraged by the operational plane, right? Like, so it feeds back on itself because our grid is going to reuse that data, those models, in order to make changes, and then it's going to feed all the way back through. Cool. So we've broken everything up, right? So we've taken this very like what we thought was like something we had to be super centralized, and we've said, cool, now we've like decomposed this finally, right? We've broken it down into its base parts, its architectural quantums. And now that we know all of this, whoops, there we go. Okay, now how do we build this data product, right? So this is important. Now, unfortunately, I don't have quite enough time to go through each one of our individual data products because normally I would go through energy consumption and we talk about what that looks like in customer household. But for our purposes, what we kind of want to do is look at our DATSs and we want to just call out capabilities, right? We just want to say, okay, in order to build this thing, what are the capabilities that I need? And I'm sure there's a lot more than this, but just generally, kind of like high level, what the capabilities are we're going to need. So in this case, we've kind of broken it down to input ports and output ports, right? Every data product has input ports and output ports. In this case, on our source aligned data product, the output ports of these data products are actually input ports to our grid consumption prediction. And so if we were to not think about tooling and just call out our capabilities, and furthermore, if we were to do this for our myriad of use cases that we have, like our highest business value use cases that we have, and also call out all the capabilities that we need, we can actually, in effect, create kind of a consolidated view. And from there, we can then understand, okay, because we have kind of this Cambrian explosion of tooling in ML and data science and also in data. And so we can then just say, okay, in order to select the tooling, I know I need these capabilities. So you can eliminate the tooling that you need just by the very base capabilities that you need. How do you know the capabilities? You know the capabilities from the data products. How do you know the data products? Those all come from a business value use case, right? You can kind of traverse up and down that tree just to validate your assumptions. Because what we want to avoid is just like the data lake concept where we just toss all of the data in the lake, regardless of whether or not we're using it, right? Who cares if it has value? Just throw it in there. Is it a lookup table? Yeah, ingest it, pop it into S3, whatever. So we want to avoid that kind of thing, and we only want to curate the data that we need and make it available that's going to give the highest business value. So if we start in that way with the business value and with the business domains, then we know that we are sure to not kind of like waste both like resources and time managing data and maintaining data that no one uses and maybe doesn't add value, right? So not all data is valuable. I know that might not be a popular statement, but there's some data that is not going to be useful for training machine learning models, for example. And if that's our business case, then we have to think about that. So in this case, of course, we have some storage. We need a feature store, a model registry, a staging storage. We have to the lower right a whole kind of Pandora's box of ML ops things. And within that, of course, we'll probably have some like CD4 ML stuff, some DVC, like so all sorts of different things that we think we need so that we can be discoverable, addressable, trustworthy, self-describing, and interoperable, right? And secure. Cool. So like I was saying, the next step in our process is the self-service infrastructure. Let's assume we had taken and done this exercise for each one of these different data products and mapped out all of their capabilities. And then we took the capabilities and kind of put it on kind of one big consolidated reference architecture, more or less, right? And we might get something, but basically what we're trying to do here is generate like some capabilities and then map those capabilities to meaningful tools so that we can create like a common data mesh platform that can be leveraged by both data scientists and data engineers. And that can also provide some like common patterns, command line interfaces, automatic provisioning of infrastructure that we can use. And so if we do that, maybe, this is very illustrative, but like maybe it looks a little bit like this. We have all of our different systems. Maybe we have, kind of an ML flow here, or maybe we have Kubeflow. So any number of things. And we have our data products at the top. And so then we can say, okay, great. This is more or less what we need to build from a platform perspective, but we also need to make sure that that platform is going to be available for all of our machine learning engineers, for our data engineers, for our data scientists, right? We need an experimentation platform. And so we need to work with the platform team so that there is self-service infrastructure. So I can, as like a machine learning engineer, go somewhere and say, okay, give me these following capabilities, and it automatically spins up the infrastructure. It gives me templates of pipelines to train CNN, LSTM models. Maybe that's a common pattern that I have. Maybe I want to do some knowledge transfer, right? If I'm constantly doing the same thing with this energy data and training it on a CNN, maybe that automatically populates for me, right? So I just get that for free. So you would notice this, and you'll notice which ones are more relevant based upon the data product mapping exercise that we did before. And you can identify common patterns in your architecture, and then you can make sure that's automated at the platform level. So it could be like a command line interface, it could be a GUI, any number of things. Cool. And finally, we have our federated data governance. So this is really key. All of the data products have to agree upon some meaningful level of output, right? So all of the schemas must live in X. And for all of the data, the quality must be measured in these 4 different areas, right? Like accuracy, completeness. For all of my models, they must measure model drifts over time, right? So, everything needs to be, either in the following formats as an output port. So that way, all of the data products, the machine learning data products, right, the consumer aligned, multiplane, can all be able to talk to each other and can be reusable to create new data products. And so this is federated data governance kind of gives you that, right? It's more like how we have, like we live in a free society, but we do have some basic rules that we still need to abide by, right? So it's not so strict that, it's going to stifle innovation, but it does need to be strict enough such that it ensures that there is interoperability, that truly the data products that you produce are a mesh, right? They can all, nodes on a graph, they can all talk to each other, that kind of thing. Great. Okay, so we talked about the kind of technical architecture, what that's going to look like. Now, if we're going to go into battle, right, we need to, like in our previous example, we had all the data engineers on one side and kind of all the machine learning data scientists on the other side, right? And so if you've ever played any games, role-playing games, that like you don't want to go in with a bunch of mages to fight a bunch of warriors, right? You kind of actually want a very diverse team. So now that we've split up the architecture, let's distribute the operating model as well. Cool. Okay, so here's where things get a little bit crazy. And I think that the reason I've kind of laid this out as a journey, because I think the easier part is actually the technical part, and the really difficult part is actually changing the socio part, right? The actual operating model, right? The people. I think this is when we encounter most of the pushback. But once everyone kind of buys into this mindset, it's actually really, really nice. And there's a lot of like cross communication with the teams, and everybody's learning from everyone else. And I find that there's more innovation. But let's say basically you have your governance at the top here, right? Pretty kind of basic stuff. You have your operational plane, so that's people kind of, maybe the business analyst or what have you. And then here, what we're going to focus in on is the per domain. So we had both of our domains that we broke down, and we had 3 different data products, right? And so, for example, with the source aligned data products, so the energy consumption and the customer household information, those 2 data products, those will have each teams. On those teams, you're going to want to put the right people, right? So like those teams probably don't need a machine learning engineer unless you decide that you also want to do, maybe you want to put a feature engineer, depending on like how you want to slice that. That would be totally fine. But basically, they're just doing that one job. They know the data. So you just want specialists to focus in on that data and be part of that team, right? Same way with the customer data, the household data, you also want to kind of just put people who are like really good. They understand that data. Maybe they need to be like, you know, more on the data engineering space as well. And so that's that team, and they provide the output ports. They publish those output ports in maybe, let's say, like a data catalog so that the machine learning engineers can find it to build different things. And that's all they do, right? So that they can be kind of a relatively homogeneous team. But then you kind of get to the energy grid's consumption. And so there's a certain amount of like modeling that's in there. There's some data science for the experimentation. There's some machine learning, right? And so all of those people, those will be specialized for that one specific team, right? And so they will operate as one team. And the cool thing is that everybody knows what everybody else is doing, right? So if there's a problem with the customer data, the machine learning engineer, you know, they know who to go talk to, right? There's no like dilution of accountability. Those are the people that are responsible for that data. If they have a question about that data, they know who to go to. There's no question about it. It's, you don't have to ask this person who may have worked on that, you know, a month ago and how did they do it and that kind of thing. No, it's that team is accountable for that piece of data. On the other side, same way with the energy, right? And finally, you have, now this is more of a shared team, right? This is the data platform. And like in our example, they're responsible for creating the self-service tooling, but basically they just provide the platform upon which these individual data product teams build their data products, right? And so they're just simply saying, okay, you know, here's your instance of Kubeflow, like, you know, here's your instance of Feast, you know, this is your namespace, you know, you take it from there, right? And they're just simply providing those capabilities so that they are able to build their individual data products. And so we'll talk about exactly what that's going to look like. Cool. Okay, so now we've kind of gotten it down to where we really need to kind of think about the problem set again, right? We kind of want to think about like, okay, what were we trying to achieve here? So circling all the way back, and then we'll talk about how that's done. So we need the more accurate modeling with the household, rapidly expand the number of households, and we need to add more sensors per household to explore additional features to use in the modeling. Okay, cool. So let's see. Right, so we've kind of built we've blacksmithed our sword, right? We have our architecture, we've put together our team, and now we're going to put it to the test. And so we can just kind of step through the different pieces here, right? So we have our 2 basic domains. We have energy over here, and we have customer over here. And in addition to those domains, so inside energy, we have our energy consumption domain, right? And so this is the team of the data engineers. They're part of this larger domain, and they know what they do. They specialize in this data. They prepare it for consumption. It goes through an ETL pipeline, and it's, you know, it's measured. It's trustable, right? It's we know the data quality, and it's what they basically do, right? And then we also have our customer household. And over here, we're just basically pumping information from a relational store where all of the operational data about customers lives, right? And we're ETLing it, we're measuring the data, we're doing quality checks over the data, and this team just focuses specifically in on that. And so we know that we can trust the data and it's prepared in nice, neat output ports. so that others can use it, and it's published in a data catalog so that others can find it and they can just re-leverage this data product, right? And if there's any problems with it, they go to this team, hey, what's going on? And then now we're also, because we have these two, which we need as inputs, we also have our grid consumption prediction with our machine learning engineers, with our data scientists, those folks, and probably data engineers as well, feature engineers, right? And so they're building the data product that we described in the original, right? The CNN LSTM. And so they're basically responsible for that and responsible for training that data. So now, instead of one central team, we've broken it up into two separate domains. They're specialists in their domains. We've reduced the friction of like who's doing what, who's accountable for what. And then also we have added a level of self-service because we've said, okay, we need data ops folks and we need ML ops folks creating this platform. Like they don't necessarily need to know about the models per se that are being built. They don't necessarily know about like what the technical pieces of the ETL that's happening, right? Like the Spark jobs or whatever. They just need to provide the cluster, provide the space, and provide tools that automatically provision the infrastructure. And so with these groups all working together, if I were to say, actually, this grid consumption prediction is great, but I would actually like to do something exactly like this, but slightly different. And I would like to use different inputs as the data, right? So then you could say, okay, no problem, right? We can scale out because we can like add another team that is dedicated to that. Maybe it's in a different domain. That team can focus in on it. I can re-leverage maybe some of the techniques that I used in the grid consumption prediction because it's available as a self-service template in my platform. And everybody knows where everything is and where to find things, right? Because I have everything's discoverable and it just like makes sense. So that's very much in contrast to kind of like our central pattern before, where kind of everyone was accountable for everything, which means no one's accountable for anything. And also, we kind of had problems with, the communication, right, between maybe the ML engineers and the data engineers. In this case, we have everybody, we're actually more focused around the business domains and the use cases so that a grid consumption prediction team has the data engineers that it needs, has the feature engineers that it needs, and has the ML engineers and the data scientists, right? And they're all working together in a cross-functional team, which is some years ago when I first started doing this, we actually, because we had such small teams, that's actually how it worked, and it worked really, really well. It was actually later that we split the two off into two separate teams. And so now we get that benefit, but we also get the benefit of scale because we know we can just kind of repeat this pattern over and over and over again. And the more we do it, the more self-service it becomes, the easier and faster the time to market. And so that's kind of the end of the story. In fact, they all lived happily ever after. Well, kind of. So until new requirements come along, but at least you have a model now that is scalable. Whereas before it was a bit brittle, tightly coupled, and it would have been hard to accommodate those new requirements that we had in terms of like adding new households and leveraging the data in a different way or different types of data and scaling out. Because now, not only because we have the platform, we can scale in different ways as well, right? And we can add more teams there, and they can be specialists in those specific areas. I think I have 5 more minutes. So if anyone has any questions, I can definitely take them now. Thanks, everyone. Have a wonderful day. Bye-bye.
Bye.